Good evening. We are now on the last part of module number 1, which is section 1.4, HDL with Verilog. So we are now on the exciting part of the module because we will start using Verilog, which is a type of HDL or hardware description language. Manual methods for designing logic circuits are feasible only when the circuit is small. For anything else that is a practical circuit, designers use computer-based design tools. Verilog HDL and VHDL are the most popular HDL language in designing ASIC or FPGA. We have already discussed that there are two common types of HDL used by companies and designers, which is Verilog and VHDL. But in this subject, we will use Verilog all throughout the discussion. Verilog syntax will be introduced in this section. Our objective is to design simple logic circuits using Verilog HDL. HDL or hardware description language. This is a computer-based language that describes, from the word itself, hardware description language. So it describes the hardware of digital systems in textual form. It means that we can write Verilog HDL using for example, a notepad or notepad++, any software where we can input text. We can use that to write our HDL code. Can be used to represent logic diagrams, truth tables, Boolean expressions, and complex abstractions of the behaviors of a digital system. So we can use this HDL to describe what we have already discussed, like the logic diagrams, the truth tables. Recall what a truth table is. It has the set of inputs, combination of inputs with the corresponding output. Or we can describe Boolean expressions with the use of HDL or any digital system. We have here definitions. Design entry creates an HDL with description of the circuit. This is just the software or the platform where we write our HDL code. Logic simulation displays the behavior of a digital system for functional testing. So this is the process where we try to simulate the behavior of the circuit. We will observe or we will test the digital circuit that we have designed. And that is of course with the help of a test bench. This is the stimulus or logic inputs used in logic simulation. Test bench is actually a code where we instantiate our design, and then we add inputs that will test our design by observing the output of our simulation. Logic synthesis. This is deriving a list of physical components and their interconnections called a netlist from the model of a digital system described in an HDL. So this is the process where we convert our design. We have our digital circuit design using HDL, And the process of logic synthesis will transform that design into the actual physical components, the logic gates. The actual logic gates that we are going to use. That is the job of the logic synthesis process or tool. It is assigning gate equivalent to the HDL design. Gate equivalent, it means the logic gates that will represent our HDL code. Timing verification, it confirms that the fabricated integrated circuit will operate at the specified speed. So this is a very important test for the behavior of the circuit. Timing verification. We want our circuit to function correctly, therefore we need to verify that the timing constraints or the timing requirements are met for the circuit to function correctly or to output the expected behavior, to output the expected output of the circuit. Because each logic gate in a circuit has a propagation delay, a signal transition at the input of the circuit cannot immediately cause a change in the logic value of the output of a circuit. Propagation delays ultimately limit the speed at which a circuit can operate. Yes, as we have already mentioned earlier. Timing verification checks each signal path to verify that it is not compromised by propagation delay. In VLSI circuit design, fault simulation compares the behavior of an ideal circuit with the behavior of a circuit that contains a process-induced flaw. We also perform fault simulation aside from timing verification. We have here an example figure where we demonstrate. This is for modeling to demonstrate the use of Verilog HDL. Let's try to convert this into its Verilog equivalent Verilog equivalent. First, let's define a few keywords that we are going to use in our Verilog codes. We have module, then the corresponding end module. This describes a circuit or a test bench, since Verilog can also be used in verification or simulation. So we have these keywords module and end module. We use that if we instantiate our circuit or design our circuit or test bench. Our test bench is also written in Verilog, but we can use other language for verification, just like system Verilog, and add a top layer of abstraction, like just for verification, like the UVM. But let's just use Verilog. This symbol, forward slash, and then asterisk, then at the end we have the asterisk and then forward slash. This is used to indicate a multi-line comment. So if we want to add comments, paragraph comments, we can use this. If we want to add a single line comment, we use 2 forward slash, then what follows is the comment. Identifiers, these are names given to modules, variables, for example, a signal, and other elements of the language so that they can be referenced in design. Starts with an alphabet or underscore, but never with a number. So it starts with an alphabet or underscore. Composed of alphanumeric characters and underscore and are case sensitive. So Verilog is case sensitive, while VHDL is not case sensitive. That's one of the difference between Verilog and VHDL. We have here an example Verilog code. Combinational logic modeled with primitives. When we say combinational logic, this is purely combinational. How do we say that? We will discuss this in the next module. Is focused on this Verilog example. The circuit is named simple underscore circuit. Simple circuit. This is the equivalent Verilog code for the circuit that we have here in this figure 3.35. The output, from the figure, we know that A, B, C are our inputs and D, E are our output. So we declare all our inputs and outputs inside this parenthesis. We have here our keywords, module and module, to denote that this is a circuit. Our circuit is named simple circuit, simple underscore circuit, with ports, inputs and outputs A, B, C, D, E. So we have here our keyword, another keyword, output, and we declare DE as output. Notice that every command is separated or followed by a semicolon. Just like here, after the module name and the ports list, there's a semicolon. Then after declaring the outputs, DE, there's a semicolon. The semicolon separates the commands in Verilog. Our output is DE and then the inputs are A, B, C. After declaring the inputs and the outputs, we have to describe the circuit. From the circuit, we have an AND gate, an OR gate, and then a inverter. We will follow the labeling indicated in the figure. W1 is the AND of A and B. Excuse. W1 is declared as a wire. There are two types in Verilog, common types. We have the wire and then register, which is reg. The keyword for register is reg. Wire, since we are implementing a simple wire, just like what is shown in the figure, so we declared it as wire W1. And then for the AND gate, the keyword is AND, and then the name of the AND gate. We'll just follow this figure here, G1. The name of the AND gate is G1. Then we declare the inputs and outputs. We start with the output. That is the syntax for the AND gate in Verilog. What's inside the parentheses is the output W1 followed by the inputs A and B. For the inverter, the keyword is NOT. Let's follow the name of the inverter in the figure, G2. So G2, the output is E, right? G2, the output is E. Input is C. So we first write E followed by C. Then the OR gate is G3. The output is D, the input is W1 and E. W1 and E are the inputs, output is D. So that's how we write a Verilog code for a given logic diagram. So we just converted this logic diagram in its Verilog equivalent. We have some definitions here. Port list, as I have already mentioned. This is an example of a port list. The interface between the module and its environment. Keywords input and output specify which of the ports are inputs and which are outputs. W1 is declared as a wire. G1 is the name of the AND gate with inputs A, B, and output W1. Verilog and any other HDL like VHDL can be used to design digital ICs. Yeah, that is in ASIC or FPGA. We already discussed that. This is the design steps. ASIC designs. For ASIC, this figure is applicable for ASIC or application-specific integrated circuit. ASIC design steps are shown in the figure above. Those enclosed inside the orange box are the scope of this subject. So in this subject, we will be only tackling this part here. From specification to RTL coding, design using Verilog or HDL, up to functional verification or simulation. So we will be only tackling this part. Let's not go to logic synthesis, place and route, fabrication, post-silicon validation. But we will make our specification, then the high-level design, low-level design. These are all parts of RTL coding. Can be considered as part. And then after creating our RTL code, we will do functional verification. This means that we will not be including timing verification. We will just test the functionality without checking the timing verification, without checking the timing of the digital circuit. But we should know that timing verification is very important if we are to actually fabricate our design. To learn more about Verilog, visit the site. Some are platforms for Verilog simulation. This site, asicworld.com, Verilog.com has a lot of examples in Verilog. You can check this website, asicworld.com/Verilog. It has a tutorial, examples. And let's go to this one, HDL bits. Some more examples in Verilog: combinational and sequential logic, writing test benches. Please check these sites. edaplayground.com, this is where you can simulate online your codes. Sorry for the slow connection. I have a lot of downloads going on. Oh, my internet. Anyway, then chipverify.com. Please download the course Verilog Software or Quartus Software from Altera to simulate circuits in Verilog offline. So, I have already given you the tutorial in using Icarus Verilog software. So let's just use the Icarus Verilog because this is light compared to the Quartus software. This is about 16 gig, 8 gig, I'm not sure. But what's nice about the Altera is this is a software for FPGA, therefore this is a corresponding hardware. You can buy the actual FPGA and test your Verilog code to an actual FPGA hardware. Gate delays. In our test bench, we usually write this line of code. What do you call this? Apostrophe? No. Tilde? Forgot. But this is, we add a time scale to indicate. For example, here we have 1 nanosecond / 100 picosecond. The 1 nanosecond here is the unit of measurement, while the 100 picosecond is the precision. So if we don't specify the time unit in our delays, if we add this one, it means that the delay has a unit of 1 nanosecond. The 100 picosecond, this will be the increments in our simulation. If we displayed a simulation, it will be, the time step is 100 picosecond. Yeah, the symbol specifies a compiler directive. It's a compiler directive. Then we placed it, for example, in our time scale compiler directive. We have here our example of another example of an HDL code. This is a gate level model with propagation delays. Notice that this is just the simple circuit, with propagation delay. This is the same circuit that we have in our first example of a Verilog code. We just added a delay for the AND, NOT, and OR gates. We have the symbol for the time delay is the sharp. So here we added 30 time unit delays for the AND gate, then 10 time unit delays for the NOT gate, then 20 unit time delays for the OR gate. Yeah, the AND, OR, and NOT gates have a time delay of 30, 20, and 10 nanoseconds respectively. 10 nanoseconds. The unit is nanoseconds. Assuming that we have added this time scale compiler directive in our code. The example below shows a test bench declaring the module's simple circuit prop delay for testing. In a test bench module, the stimuli A, B, C are declared. So let's take a look at the test bench example. This two forward slash are comment directives, right? Recall that this is for a line comment. So we add this comment test bench for simple circuit prop delay. This is our test bench. So we declared our circuit simple circuit prop delay, and we named it M1, and then instantiated the ports A, B, C, D, and E. Excuse. And we added a comment. Don't forget the semicolon. Excuse. Then we have instance name required. We added this comment instance name required. Module and module, we declared wires DE and the registers ABC. In a test bench, the output, we know that the output of our circuit, the circuit that we are going to test, is D and E. And then the inputs are ABC. This wire DE and register ABC, these are different from the ports list here. You should not be confused. We can rename this. We can use any other name instead of DE and ABC. This is for the test bench itself and not from the circuit that we designed. This is for the test bench. And then notice that for test bench, usually the inputs that we are going to connect to our circuit under test are declared as register. So we declare as register A, B, and C. This is the input to our circuit or design under test, DUT. It's usually called as DUT or design under test, or DUV, design under verification. We assign A here. It assigned the inputs A, B, C with 0, 0, 0. Then after 100 time unit delays, it assigned A, B, C the values 1, 1, 1. Then notice that if we assign values to our stimuli A, B, C, we put them inside an initial statement, and this initial statement is followed by begin and end. Between those keyword begin and end, we place our stimuli, the stimuli for our test bench. And then if we can also declare another initial statement. Here it did not write begin and end because this is just a one line of command. It has one semicolon to indicate that there's only one line of command, which is just a $finish statement. This means that the simulation will end after 200 time unit delays. Actually, we can write this $finish statement inside this initial begin. The difference is if we place this $finish statement here with a 200 time unit delays, then it means that it will end from 0 to 200 time unit delays. If we place this sharp $200 finish statement inside here after this statement, then the whole simulation will end after 200 plus 100, so 300 time unit delays. So that's the difference. This is an example of the simulation output for this test bench. Notice that ABC is assigned 0, 0, 0, and then after 100 nanoseconds, ABC changed from 0 to 1. And the output, look at the output, D and E. Notice what happened here for D and E. Let's check the circuit. Not or and. 10, 20, 30. It's not clear here anyway. So this is the behavior of the output. Should we still check? Okay, let's check. By looking at the logic diagram, D is equal to C prime. Let's write down. D is equal to C prime. This is C prime or AB. Then E is equal to C prime. Let's check that to our test bench. Let's go here. When A, B, and C are all 0, when A, B, C, let's write the truth table, are all 0, what will happen to D if this is 0? So D is 1. Then E, C prime, 1 also. If all are 1, 1 prime plus 1, 1. D is 1, then E is 0. So if here, this part here, where A, B, and C are all 0, D is 1, E is 1, correct? Here, when 1, 1, 1, Let's go to the time when all the inputs, all the gates are stable. Not this part here. Let's go here. When all A, B, and C are 1, 1, 1, then D is 1 and E is 0, right? This part is 1, so this means that this part here, E is 0. 1, 0, which is correct. 1, 0. If you ask what happened here to our D, because of the delay that we have added to the gates. So D is affected by the delay for all of the A, B, C, and D, while E is affected by the delay in the NOT gate. So D is affected. E is affected by the delay of the NOT gate, which is 10 nanosecond, right? 10 nanosecond delay. So when the inputs ABC change from 0 to 1, the output E did not change immediately. It changed after 10 nanoseconds delay, which is this part. And then the output D did not change yet. After 10 nanoseconds, it did not change yet, because if we have this, we look at D. Look at the logic function. Wait, of D. What happened to my C prime, this part here, C prime, the inverter, when ABC are 1, 1, 1, so D is 0. So D is supposedly 0, but we have this AB, which is still 1, 1. Anyway, let's not try to go that much deeper, but the thing is that after 30 nanosecond delay, that is when our output D is already stable. So in this part here, that's when our output is stable, because that is the maximum or the longest propagation delay of our logic gates, which is the AND gate. This is 30 nanosecond delay. So our output is stable at that propagation delay. That's the effect of the delays in our logic gates. If we measure the output when the signals have not propagated yet, then we are going to get the wrong output, the wrong or expected output. We need to make sure that's why timing verification is very important Otherwise, the circuit will not function according to how it was designed. Assigned keyword can be used to create combinational logic, non-sequential circuit. For example, we have here assign D is equal to A and B or not C. So we use the keyword assign. We describe the circuit. Let's erase this first. We design this logic function D is equal to C prime plus AB with the use of the assign keyword. Assign D is equal to A and B. Since this is a logic function, that's how we write and the two ampersand signs, then we close it into parentheses, and then this is for OR, logic OR, equivalent to the plus or here, and then not C for the inverter, then add a semicolon. HDL Example 3.4 describes a circuit that is specified with the following two Boolean expressions. E is equal to A or BC or B prime D, and F is equal to B prime C plus BC prime D prime. The equations specify how the logic values E and F are determined by the values of A, B, C, and D. So let's check the example 3.4. So it implemented these Boolean functions for E and F. We add the keywords module and then end module, then the name of the module. Our circuit is circuit underscore boolean underscore CA. Then we declare the ports EFA, BCD. We declare the output, which is C and F, and then the inputs A, B, C, and D. And then we use the assign keyword to denote the combinational circuit E. So this is how we write it. E is equal to A, and then this is for the OR, then B and C, double ampersand, and then another OR, not B for the complement of B, and then we end that double ampersand with D. Then don't forget the semicolon. For F, the same. Assign F is equal to B prime, which is exclamation mark, and then B, then double ampersand C, then we OR that. So take note of the parentheses. We OR that with B and C not, then ended with D, not D. And module. That's how we use assign keyword to denote combinational logic Boolean functions such as E and F in this example. So from example 3.4, E and F are evaluated using assign keyword. When not specified, the signals are assumed to be of wire type. Let's check again. We did not put wire here. We did not declare any wires. But it is assumed it is how do we say that? Just assume that the outputs E and F are both wires. When we are dealing with combinational circuits, usually it will be wire type. Here A, B, C, D, E, and F are all of wire type. Register type are used in sequential circuits, where timing depends on a clock signal. Combinational circuits don't rely on the clock signal, so that's the difference between a combinational circuit and a sequential circuit. Notice that in combinational circuits, just like this, there's no clock signal, right? We are just connecting the signals. That's why we use wires instead of registers. There's no clock signal here. We're just connecting the circuits using wires and then logic gates. So that ends our discussion in section 1.4, which is about HDL with Verilog. That's the last step. It's not the last topic. We have our last topic, which is 1.5. Levels of modeling or abstraction in Verilog. Let's tackle this shortly. Then we're done with module number 1. This section we will briefly discuss the levels of abstraction in Verilog HDL. This will give us the bigger picture as to what approach to use in applying Verilog to design a digital circuit. Our objective is to enumerate and explain the levels of abstraction in digital circuit design with Verilog HDL, and then differentiate synthesizable and non-synthesizable codes. Verilog supports designing at many different levels of abstraction. 3 of them are very important. So these are the levels of abstraction in Verilog. We have behavioral level, then the RTL or register transfer level, and then the gate level. Behavioral, this level describes a system by concurrent algorithms, or behavioral. Each algorithm itself is sequential. That means it consists of a set of instructions that are executed one after the other. Functions, tasks, and always blocks are the main elements. There is no regard to the structural realization of the design. Then RTL, register transfer level. Designs using the RTL, register transfer level, specify the characteristics of a circuit by operations and the transfer of data between the registers. An explicit clock is used. RTL design contains exact timing bounds. Operations are scheduled to occur at certain times. Modern RTL code definition is any code that is synthesizable is called RTL code. So, over the years, the meaning of RTL has changed. Presently, RTL code now denotes or refers to any code that is synthesizable, because sometimes we get confused with whether we should call our code or design RTL code even if it has behavioral codes in it, because digital designers that use RTL are using behavioral and RTL levels, both behavioral level and RTL level. So they design in these two levels of abstraction. Anyway, the definition of RTL code now is is any code that is synthesizable. As long as it is synthesizable, we will define it later what this term means when we say the code is synthesizable. Gate level, this is done automatically by the tools, software tools already. The examples that we did actually are these examples where we use and, or, and not gates. That's an example of a gate level abstraction. But digital designers, RTL designers, use behavioral level and RTL level. The gate level is done automatically by the synthesis tool. Unless there are errors or problems in synthesis, then you have to look at the result and try to correct the errors in the gate level. It is important to consider whether the code written in Verilog is synthesizable or not. Synthesizable code in Verilog means that you can implement it in the actual hardware using actual logic gates and resistors. If we can't, it only means that your code must be synthesizable. Otherwise, it will not be. There's no actual hardware equivalent, and therefore it can't be fabricated or manufactured if it's not synthesizable. I mean, what's the use of your code? What is the use of your code if you can't synthesize it, if there's no actual equivalent hardware? The meaning itself of HDL is hardware description language. Therefore, we describe a circuit using HDL, such as Verilog or VHDL. And if we can't have an actual circuit with our HDL code, our circuit is useless. So do research on synthesizable and non-synthesizable Verilog constructs. Please do that. Why are there even non-synthesizable Verilog constructs? These are actually used in the test bench. Those non-synthesizable Verilog keywords or codes, they are used in verification or testing our HDL codes. So use only those synthesizable Verilog constructs for your actual circuit, for your circuit design. And then use the non-synthesizable for your test bench if you are using Verilog for your test bench. If you are not using System Verilog or UVM and you're just using Verilog for your test bench. Gate level. Within the logic level, the characteristics of a system are described by logical links and their timing properties. All signals are discrete signals. They can only have definite logic values 0, 1, X, and Z. Do you know what X and Z means? Z is high impedance and X is undefined value. Z is high impedance. Usable operations are predefined logic primitives and or not, etc. All those logic gates, they are called logic primitives. Using gate level modeling might not be a good idea for any level of logic design. Gate level code is generated by tools like synthesis tools. As I would have already said, And this netlist is used for gate level simulation and for backend. As what I have already said, the gate level code is generated automatically by the synthesis tools from your HDL, behavioral, and RTL codes. And this will be used in the fabricating part, in timing verification, and it's called backend. Design, RTL design is front end, and then there's timing verification, gate level part is back end. In gate level, the modules are already in terms of logic gates. RTL has a higher abstraction, therefore it is the upper layer of the abstraction level. Hence RTL and behavioral. All circuits designed with Verilog will eventually be translated to the gate level, where actual gates are specified in the modules. So I hope it's clear what the difference is between the three behavioral level, RTL level, and gate level. These two are used by RTL designers. Gate level, usually this is automatically done by the software tool, and you check the gate level during your timing verification, and if you check for errors or warnings during synthesis. That ends our discussion for module 1. Our next topic is module 2, which is about combinational logic. Thank you for watching. See you on the next video.